Okay, so we're back, October 8th, 522, and this is part two. Okay, so before the break, we talked about bootstrapping. And as you think about the bootstrapping approach a little bit more, um, you see that a lot of it depends on the goodness of your original sample, right? So, when you think about it, figure, boy, that first sample better be good. Because if I'm sampling from a population, if I'm sampling from a population, I'm then going to sample from the sample. Right? I'm then going to sample from the sample and get sample one, sample two, sample three. So I'm sampling from the sample, but originally I have to sample from the population. So this sample better be good, right? Because if this sample is completely biased and you're like handpicking this sample, and you're saying, let me, if I want to study, how much variability I have in vaccine responses for COVID, well, let me pick people who seem to be reacting pretty well and look pretty healthy. Well, that's completely biased sample. So this sample here should be drawn in a random way, and it should be a healthy sample. Healthy, but what I mean, it has to be statistically a good sample before you basically exploit the sample, right? First choice again, right? At least in theory, first choice would be to sample directly from the population. But the thing is that if you have the population information, why don't you just compute the estimate of the parameter? So in our case, that was that fraction we were talking about. Why don't you just compute the number, and then you don't have to do any sampling at all if you actually know the population. So again, what you don't want to do is end up with, saying that, I have population data. Wow, I'm going to do the first choice, and then you're bootstrapping from the population when and going through all this trouble when all you have to do is really start just computing parameters on the population. So again, you got to make sure that you have that big picture of where this stuff works. Otherwise, you end up doing something where it looks sophisticated, but you actually don't even have to be doing it, and it's not even ideal. Because then the question becomes, why are you bootstrapping directly from the population and instead of just computing the coefficient on it? The only way the bootstrapping really works, right? The only way it really works is that if you're having to get a sample from the population, because this is the indicator of uncertainty, right? We don't know that sample. We expect sample to sample variability, right? So this is kind of how good is that sample? How much variability is really going on? Well, since we can't have access to the population, let's just keep sampling from the sample, and that's what it does. So again, if your impression is when you look at that, and you may have the impression, well, wow, that's kind of like, it's almost like double dipping on the data, right? It's like you're sampling over and over of the sample you got. It's like sampling 5 people and then sampling those 5 people over and over. That's exactly what the bootstrapping is doing. So you can kind of see that it is double dipping, and you're making a lot of use of that original information. So again, this information better be good. It better be a good sample, otherwise the whole thing isn't going to really work very well. Okay, so let's talk about chapter 6, get into chapter 6, and also preview a little bit of where we're headed to next week, which is going into principal components analysis. And we need a little bit of that to understand this chapter. So we know what the linear model is, and where we're going with this is this idea of regularization, okay? So model selection and regularization, what does it mean to select the best model? Okay, the topics of this chapter are actually really, really important when we start talking about the best model. And the best model, as we're going to see with all things statistics, is choosing the best model depends on how you want to select the best model. And I know that's kind of frustrating because you're like, I just want to know how to get the best model, right? Well, what determines the best model is going to be a certain function of the data. And there are different functions of the data that are advertised for generating the so-called best model. So the best, here's what I'm going to say. The best case scenario, okay, the best case scenario right from the start is that if you're trying to get the best model, You're never, ever going to be able to say to an audience, I found the best model. Never going to be able to say that. What you're going to be able to say, the most you're going to be able to say, is that I found the best model in this particular sense of choosing the best model. Okay? So what I mean by that is when you advertise a model, you have to describe how that model was produced. And that's, I'm not saying that you can't get like a really optimal model. You can, but you should always describe the function that you used or the measurements you used to arrive at that so-called best model. And the reason why I say that that's usually the best that we can do is because there's so many alternative ways of approaching the problem that oftentimes you have to look at in terms of what's the function that produced it. And again, that's why the theory is so important, right? You can sometimes you can say, well, the theory isn't important. Well, the theory is important because the theory is determining, in this sense, what conclusions you can draw about the reality, right? So when you're thinking, is there something going on in my data? Well, it depends on how you define that theoretically. So the theory better be good, right? The theory better be good. The analytical method better be good. It better make really, really good sense for you to conclude something about reality. Okay, it's not like an archaeological dig. Okay, so there's the archaeologist, and they're digging into the hole, and there's something in the hole. Okay, there's like there's a skeleton. Okay, in the hole, and when they dig inside the hole, they find what's there, and then someone else comes around and they kind of confirm it, say, yes, look what you found. You found something in the hole, right? Well, that's kind of like a pretty conclusive statement, right? There isn't any kind of debate over, well, how are you looking at it, right? What eyes are you using to look at that skeleton? What eyes are you using to look at that skeleton? It's kind of just a skeleton, and we can kind of get on with it. Now, where theory does enter here is there's going to be a whole bunch of, theoretical background to this person and theoretical background to this person. So this person looks at the skeleton, may draw different conclusions about it compared to this one. That's kind of like the same thing we're talking about here when we're talking about getting the best model. Kind of depends on how you look at it. And that's where the theory would come in with the two researchers doing the archaeological dig. Because this person's going to say, hey, this person was like, this is like 20,000 years old. And this person's like, this is like 100,000 years old, based on my theory of what I'm seeing on the individual, or my theory of fossilization or what have you, and all that stuff. So that's where that kind of goes into here. But the archaeological dig, there's no question that they could both agree that they found something. But after that, you kind of go into what exactly did you find? Kind of also true when you think about climate change and stuff like that. If that's the reality, well, look at how many models there are for climate change. Just think about it, right? Just for a second, you hear things every day, and there's a whole bunch of research out there saying, well, this is what climate change is. This is, how much climate change is there? Is there climate change at all? All of that stuff often goes back to, you can't just look at the reality. It's not just in the data, because the data is almost the same for everybody, right? Even though you can have debates on what constitutes good data, but the data is the data. It depends on what analytical method, what theoretical method you use to analyze the data. So what's the best model for climate change, right? What's the best model for climate change? How should you select the best model? Comes down to understanding the theory well and making judgments based on that. So in this chapter, we want to look at how to select the best model, which also means how to select the best predictors. Predictor importance, variable importance. Okay, the topic of the recent assignment was a big thing on how do you get the variable importance. What does it even mean to say a variable is important? Well, there's our variables in our linear regression and our multiple regression, all our different variables up to the p variable. So which one of these is going to be most important? Well, the first thing we need to talk about is whenever you build a model, and this is something I talked about in one of the assigned papers that was assigned, was As soon as you select the predictors from a wider population of predictors, so you can have a wider population of predictors. There's X1, there's X2, there's X3, there's X4, there's XP. It's almost like the bootstrapping idea. It's not the same, but it's almost like it, right? Like you're sampling from the population. It's going to be a bias sample in this case, but you're going into the population of potential predictors and you're producing a subset of them, right? You're producing a subset. These here, candidate predictors. Okay, that's my term. Candidate, not term, predictors. They're candidate predictors because these are the predictors that you're going to use to build your model. So remember when I just said in the bootstrap example, I said what? I said the importance of this sample cannot be overestimated. Why? Because you're going to be producing estimates based on this sample. That was in relation to bootstrapping. Kind of similar here, that if you're going to choose the best model and have any sense of measure of variable importance, then boy, it better be good, right? That's the most important part. If your bootstrap sample earlier up there, if your bootstrap sample was ridiculous or like hand-picked and you were selecting all people coughing and having fevers to evaluate vaccine performance and all that, it's going to totally ruin things no matter how often you sample from it. Well, it's the same idea here, only here we're in a strong sense sampling predictors. So what's the big picture? The big picture is that if you're going to produce a model and try to determine which predictors are best, the most important part of all the modeling process is making sure you get this right. Right? Making sure that what you sampled from the population of potential predictors is good. It's theoretically accurate, and it exploits your knowledge of the area. So this is based on not statistical criteria. This is based on your knowledge. And no statistical mechanism could ever do this for you to get the right candidate predictors. What's that related to? That's related to model specification. Right? Now, we haven't chosen the model yet. We haven't built the model yet. We've just said these are the candidate predictors we're going to consider for inclusion into the model. But recognize that's the most important step. You can do your dissertation on certain predictors, and the whole kind of thing can fall if you didn't include this one. Because boy, if you're going to build a model of COVID, but you did not include pre-existing conditions, then whether you're using a stepwise approach forward or what have you, on your candidate predictors, your set is wrong. Your set is misspecified. Why? Because you left out pre-existing conditions. And we know so far that pre-existing conditions have a huge impact on outcome of COVID. So you see the analogy, right? You see the analogy there that getting this set is really important. That's why you can think of it in terms of all COVID models are wrong. All forecasts of COVID, back in March when they were forecasting how many deaths would happen. Do you remember when they said we'll have about, in the US, we'll have about 80,000? They said about 64, and then they went to 80,000, and now I think we're up to 200,000. Now, to be fair, they also didn't completely say 80,000 or 64 into October, I don't think. But these estimates ended up being pretty low. Why? Because they probably didn't have all the candidate predictors. There's probably a whole bunch of other things that were influencing the response that they did not include. Probably because they may not have known what those are. So the biggest part of model building is trying to get a handle on this, which means knowing your area, knowing your literature review, knowing your sources, and trying to get this right. So what I like to say is, spend 10 months trying to get this right to build a good model, and then another 10 months doing the analysis and writing it up and looking at your data and all that. Maybe not 10 months, maybe a little bit less, but you get the idea. Okay, so selecting best predictors is really hard. The other idea too is when you select which predictors are best or most important, you're doing it within the context of the model you've chosen. So again, it's not the same as bootstrapping, but boy, the analogies are there, right? Because you've got population, you got your sample, which is hopefully you're sampling this based on, it's not a random sample. You're sampling it based on your expertise. But then now the question is determining importance of those candidate predictors that you're including in the model. So you get your candidate predictors, you build a model, and then you have to assess importance of that. So when we talked about bootstrapping, and I said, boy, you're really exploiting your sample. You're exploiting your sample, and it's like, boy, how much can you use your data, right? Well, that's kind of like what you're doing in your model building. So you're getting a very simplified version from a very wider field of potential predictors. What this might remind you of something, might remind you of the ideas of like partial correlation, zero order correlation, that we know that the partial correlation is not equal to the zero order correlation. And you can think of it in terms of this process. Don't leave out any good variables. Specify your model really well, because otherwise all of your parameter estimates will be off. All of your regression coefficients will be off. They'll be biased, and you're also misleading your audience because you're not including the relevant variable of like pre-existing conditions. But your audience, they'll be knowledgeable about your research, and they'll point that out to say, how can you build a model without pre-existing conditions? And so you have to answer to that, right? That's up to you as a researcher to make sure that that's done. And again, that's not a statistical question. That's not a statistical, it's more of knowing your model, knowing what's important. Right? You're not gonna predict suicide rates without including the measure of depression, or maybe alcoholism and things like that. And that's where people are going to comment on saying, you're leaving out important predictors. And in the statistical sense, it's because it's biasing your other estimates. Okay, so we want to select the best model. So that's where we're going with this. We want to select the best model, and we want two things from our model. We want prediction accuracy. Okay, we want prediction accuracy. And we also want model interpretability. So those are kind of those two things. The least squares estimates for the linear least squares usually has pretty low bias. That's if the relationship is approximately linear. So if you have an approximately linear relationship in the population, as we've mentioned before, that has actually pretty low bias, and the linear equation is actually pretty darn good. It does a nice job if the true relationship is linear. If it's not, right, then you're in trouble, right? But if your n is much greater than p, the number of predictors, with n is the number of observations, so you've got a good sample, in other words, then your least squares tend to have low variance and hence will perform well on the test observations. So it's usually pretty good. So you may question, like, why look at different options then? Why look at different options? Well, in some situations, especially when your n is close to your p, so you don't have that big of a sample, you're going to have a lot of variability in the least squares fit. You're likely going to have a lot of variability in that least squares fit. So if you're fitting your line to like just a few observations, well, we know that if I put another sample to this, maybe the observations do this. So boy, that line doesn't look quite as good anymore. Right? So it's not a good, doesn't give good predictions on future observations because you've trained it on so few, right? So there's going to be a lot of variability here. If p is greater than n, then you don't have a unique solution, okay? And that you cannot estimate those parameters properly. And I mean, the software will just kind of blow up, and don't worry, you'll know it. If those things happen, the software says they cannot do it. So what do we want to do here? The variance is infinite, which kind of is a very strange thing to say, right? The variance is infinite means that you cannot even know the variance of that method because p is greater than n. So one possibility is to constrain or shrink the estimated coefficients. And when you do that, you reduce the variance at the negligible increase in bias. So this here is actually a pretty important statement that we will develop most likely next time. But we reduce variance for an increase in bias. So remember the variance bias trade-off, right, that we looked at before. What this deals with is we're going to purposely, right, we're going to purposely introduce bias. We're going to purposely introduce bias into our regression in order to reduce the variance a little bit. So up bias, down variance. And this goes against almost everything that you've likely learned in statistics before, because everything you've learned in statistics before says, hey, unbiased is best, right? So when we did this, when we took the expectation of the sample mean, and we said it's equal to the population mean, and we applauded this result. We said, this is great, because the expectation is equal to the parameter. This is unbiased. Well, in the analogy here, now we're going to do something like this. Again, only by analogy when I'm using the sample mean. I'm going to do something like this. I'm going to say, instead of using the sample mean, say the sample mean plus, say, pi over 2. I'm making this up, but I'm adding something. I'm altering this estimate so that the expectation of this is no longer equal to this. I'm purposely messing it up. And I'm messing it up, so I'm purposely increasing bias to reduce some variance. That's the analogy to this simpler situation. The other issue is model interpretability. It's going to help us to kind of maybe work through some of these techniques, because you might be able to identify irrelevant variables. And we're going to see that this shrinkage method, okay, this constraining or shrinking, is actually going to help you make decisions on variables within the model you've chosen, that you've chosen to model around your candidate predictors. Again, candidate predictors is all it can do. These statistics are not like, they can't go back into your population of predictors and say, hey, you forgot about this one. You forgot about age. Age has a big influence on outcomes for COVID. It's up to you to include that. But once you have those variables in, this model selection technique or these regularization techniques are going to help you identify irrelevant variables within that particular context. Okay, within that particular context. Sometimes these things are called features. They're variables. This is the same thing. So when you hear the word feature, it's just kind of it's like a dressed up word on variables. Maybe some people think it sounds better, but it's the same thing as a variable in this context. So there's many different alternatives to model selection. We'll talk about the subset selection in a second. We've talked about shrinkage a little bit, about what that is. And this is, going to be the first half of next time. We're going to fully delve into shrinkage. And the other thing that we're going to start developing, if we have some time today, we may not, is this dimension reduction technique. And this is related to the principal components we're headed to, also hopefully getting into next week. And what does principal components analysis do? Well, we're going to look at the whole chapter on it coming up, but it involves projecting the P predictors into an M-dimensional subspace where M is smaller than P. Now, what does M smaller than P means? It means you're going to take a matrix of variables, x1, x2, x3, let's say, up to xn, x1, x2, x3, and we know that this matrix has a rank of 3, right? If all of these are linearly independent of one another, then the rank is equal to 3, right? If these are all linearly independent. Well, what is principal components analysis going to do? Principal components analysis is going to do is going to say, do you really need these 3 variables to express the information, to be more specific, the variance in these variables, right? The variance in these variables, because you're going to have a variance here, a variance here, and a variance here. The sum of variances, the sum of all of those variances is, in this case, the trace of the matrix, because it's the sum along the main diagonal of the matrix. So what PCA is going to do is it's going to look at those variances and try to see if you could reduce the rank. So instead of expressing the variance by having 3 dimensions, we're going to try to reduce the rank into maybe 1, maybe 2. And we've talked about that idea before, about this idea of principal components and an orthogonal translation on the data and linear combinations or projections. We're projecting onto a new thing, a new variable that we're going to call the principal component. The way this is used in this idea of getting the best model is those projections. So, let's say that instead of rank 3, you end up with one component that you want to keep. It's going to produce 3 components. But let's say you end up with one component that you want to keep, right? One component. Well, you're going to use that component, right, from this big process here as a predictor to fit the linear regression. So instead of your linear regression looking like this, x1, x2, x3, predicting y, you're going to work on this in a principal components analysis, and you're going to use maybe just C1. And C1 is going to do this, and C1 is going to maintain most of the variance in x1, x2, x3. And that's going to be this idea of dimension reduction, because you're reducing the dimension of the data, the dimension of the number of variables you need, and you're going to use that reduction in dimension as a predictor in your next analysis, and that's how that's going to work there. Okay, but this here, recognize that this is like a whole chapter that we're going to be looking at. So though we'll talk about the dimension reduction in the context of best model fit, we still have to develop that stuff in an entire chapter, which involves the eigenanalysis and those things. So let's just run through this a little bit. The best subset selection. Well, the best subset selection will fit a separate least squares regression for each possible combination of the P predictors. Okay, each combination of the P predictors. So we fit all P models that contain exactly one predictor, all P2 models that contain exactly 2 predictors, and so forth. So the first thing when you think about best subset selection is that's going to be a lot of models. It's going to be 2 to the P possibilities considered by the best subset selection, and this number of models is not trivial. So it's going to be actually a lot of models, especially if you imagine like big data problems where they have like 1,000 predictors and they're trying to look at that. I mean, the number becomes like you're in the millions of models. So oftentimes we don't talk about computing speed in this course, and we don't talk about like how much can the computer handle, because for most projects our computers are sufficient. But in some cases, when you have a lot of variables and data, it can actually be a really hefty task. So sometimes when these authors are saying that's computationally not feasible, they're not always just being like idealistic. They're actually saying this is actually a problem when you're working with big data. So M sub 0 denotes the null model, which contains no predictors. That's the model that contains no predictors. This predicts the sample mean for each observation. Then you're going to fit all P, choose K models that contain exactly K predictors. And you're going to pick among those and call it MK. Here, the best is defined as having the smallest residual sums of squares, or equivalently, the largest R squared. And those two are going to be the same. You're going to reduce the residual sums of squares. That's the same thing as maximizing R squared. Now, how do you select from all those models? So imagine you got like 100 different models, right? How are you going to select from these? Well, what's the first guess, right? What's the first guess? What's the first kind of thing you think? You say, well, I just get the one with the highest R squared, right? First impression is, imagine you've got 100 models, and then you had them all listed, right? Model 1, Model 2. There's the report for Model 1, Model 2, Model 3, Model 4, Model 5, etc. You say, hey, select among these which is the best. Well, doesn't this seem like it's almost like a foolish question? You may say, well, just go with the largest R squared, right? Because this is going to spit out an R squared. This is going to spit out an R squared. Okay. So why do we even need all this stuff here? Why don't we just choose one with the largest R squared, or in other words, the smallest RSS? And the problem with that is that approach is going to be faulty, because what happens as you add predictors to a model? The R squared always increases. The R squared increases, the residual sums of squares decreases monotonically. In other words, it keeps decreasing. It keeps decreasing and the R squared increases. So as you add predictors to the model, you're increasing your R squared. And you may know that from our previous class, and we may have even talked about it in this class a little bit, that you're adding predictors, your R squared is increasing, so we cannot use that as model selection criteria. Okay, let me give you an extreme example of this. And sometimes you'll see this, you'll see like a research paper, that has like 10 or 15 predictors, right? So you've got like X1 all the way to like X15. And then, the authors or whoever's presenting the model says, this is a great model, right? And they say, this is a great model because R squared is equal to, 0.15, right? The R squared is equal to 0.15. 15% of the variance is explained. What's the problem with that, right? You need to be able to critically evaluate and say, okay, this is not that meaningful. Yeah, you're explaining 15%, but it's like on average, this is 1%, this is 1%, this is 1%, etc. And you know that it's going to increase. So the problem with the hierarchical regression, let me just try that one more time. Hierarchical regression is that your R squared is always going to increase. So, if you add a predictor to your model, say, look, I experienced an increment in R squared, that's not surprising. You're going to experience the increment in R squared. Now, whether it's a statistically significant increase, you could test that out, but this is not impressive. This is much more impressive if you're only using 2 predictors. So we're going to need a cross-validation method that's going to, help us adjust this based on kind of the logic I just explained here. And those will be called CP, AIC, BIC, and adjust R squared, which we're already familiar with. And we'll look at a slightly different formulation that they present over here. But always remember this idea, right? That's why you got to look at a model. You can't just look at the statistic. You can't just look at the R squared. You gotta look at the model in entirety and say, what's going on here? What's the big picture? How many predictors do I have? What's the value of each predictor? And so on. So here's an example of residual sums of squares for a particular simulation. As the number of predictors increases, well, the residual sums of squares gets, pretty small over here. It keeps going down a little bit. And here it keeps going up a little bit for the number of predictors for your R squared right here. Again, we're going to be looking at these different approaches for model selection, and these approaches for model selection are going to be based on the particular sample on which you built your model. Okay, so we're not using a cross-validation approach here. We're not like sectioning out some of the sample and doing like a leave one out thing or anything like that. We're actually analyzing our sample data that we fit the model on, and we're computing these measures to try to adjust things for us a little bit and say, well, how do we know we're not just exploiting our data and artificially creating a good model fit? Stepwise selection. This is kind of just review. When we talk about stepwise, we're all familiar with how stepwise works in terms of like maximizing the squared semi-partial correlation in terms of an incremental test for forward selection. This is another stepwise algorithm that you fit all the models that augment the predictors in MK with one additional predictor, and then you choose the best and call it MK plus 1, and the best model has the smallest RSS or highest R squared. So then you select it using cross-validation. So in this case, you're adding on the different predictors. Now that's not entirely the same thing as the stepwise that you may be familiar with the squared semi-partial correlation. But it's the same idea that you're looking at adding predictors to it and looking at which one fits the best. But this one, you're using these measures to help determine that, not just the pure maximization of the R squared, as you would have in some versions of stepwise that most of you may be familiar with, where you're maximizing that squared semi-partial correlation and just stopping when nothing adds to the model, right? When there's no more statistically significant predictors, the model stops. Well, this one, a little bit different because you're using a little bit better model selection criteria. Okay, so SPSS version, they're not doing this. They're not looking at these measures. They're just looking at the statistical significance of that additional predictor. And if it doesn't predict statistically significantly, then the model stops and you stop with the forward regression. Let's just continue here and get to the backwards stepwise selection. Well, that's when you start with all the variables and then you reduce the number of variables. So you can look at that. Again, a little bit different than how SPSS is doing it, because we have these indicators now that we're looking at. You get the hybrid approaches, right? And this is like the pure stepwise approach, right? So what we just looked at was forward, and we looked at the like the backward. Well, this is, you know, the pure stepwise, so a hybrid of forward and backward. This is the kind of like the SPSS pure stepwise algorithm, where you're selecting, you're kicking some variables out, you're selecting, and that's forward and backward stepwise. So after adding each new variable, the method may also remove any variables that no longer provide an improvement in the model fit. There's some disadvantages with this approach, right? And you may have heard in previous class, those who've taken it with me, stepwise regression, be very careful with that, because it could boot out an important predictor. And those model selection approaches that we're looking at here with the forward and the stepwise, like what SPSS does, doesn't always end up with being the absolute best model either. All it ends up doing is maximizing the algorithm, right? It's not always the actual best model. So there's a lot of things to not always like about those, even though they're in popular use. You can be a bit critical about those approaches, and many authors are. So how to choose the optimal model? Well, we've mentioned this before. We said it's a big problem. Getting the optimal model, especially with this candidate predictor business, it's not easy. Variable importance almost becomes like an impossibility when you consider the candidate issue. So, if you're going to assign variable importance, maybe the best way, or the most idealistic way, let's say, because you have so many possible variables out there, is imagine if you could, hold all the variables out there constant, right? So hold everything constant except for this variable, and there's your experiment, right? That's exactly what the experimental design does. And it's kind of advantageous to look at the experimental design in the context of the optimal model, because then all of these things are being held constant because of this simple thing, random assignment. You're going in the experimental group, you're going in the control group. When we do that random assignment at this decision node here to randomize, what that's doing is it's holding all these predictors, right? All these variables constant, because this individual going in the experimental group and this individual are only purposely different with whether they've gone to the control or experimental. Now, there's a lot of differences between the individuals, right? There's a lot of differences. So I'm not saying they're all the same necessarily on all this stuff, but it's our best shot at it, right? I hope that makes sense, is that all of these, variables in the universe, they're going to differ on all those, but we hope that all those differences balance out. And the random assignment to groups is our best shot at making sure that balances out. So what I'm hoping also comes from this discussion is, in trying to get the optimal model, you see how hard this is. See how difficult this is, because you've got all this like bias going on and candidate predictors and all this stuff. The experimental design attempts to alleviate all of these issues we're dealing with. And it kind of gets us out of a lot of this discussion if you can just get that random assignment to groups possible. Very hard to do in some contexts, right? In some contexts, you definitely can't do it. And sometimes it just doesn't even make sense to do it. Like predicting the number of deaths from COVID, how can you randomly assign? I mean, it's impossible. So doing an experimental design doesn't even make sense. Although getting the vaccine for COVID definitely does. Because if you don't do this, then people can differ on all of these other things, and you don't know whether the vaccine is the thing that's having the difference, or if it's all these things. But still, they're still doing model selection too. What's the best model? What's the best model for COVID? What's the best model for the number of deaths? It's all related to this. You can't separate the experimental issues, right? The scientific issues from the statistical model. Okay, so how are we going to do this? Well, how do you estimate the optimal model in this context? Is you make an adjustment to the training error rate, accounting for the bias due to overfitting. So you've probably overfit your model to some degree. So let's estimate based on the training error. Again, you don't have to do it this way. You can also do it estimate that test error directly by doing the cross-validation that we've talked about in the previous chapter. So, but in this context, we're going to adjust the training error rate so we can have some kind of a reflection on the test error rate. Now let's look at a few of these measures. These are very useful measures, and you're going to see them in almost everything you do. It's adjusting the training error rate. Mean square error is residual sums of squares over n. So remember, when you're doing a regression, just spot where these quantities are being taken from. Right? So you've got your reg sums of squares, you've got your residual SS, then you've got degrees of freedom, right? Degrees of freedom, while residual sums of squares over n is your mean sums of squares error. Okay? So you're getting your MSE over here. Now this estimate right here is they have to subtract by your degrees of freedom to get the unbiased estimate. They're just saying MSE is a residual sums of squares over n. They're not losing degrees of freedom here. A little bit of a difference of what they're doing here. Our estimate of MSE will have to lose the degree of freedom. So SS over degrees of freedom equals MSE over here. So we want to adjust the training error rate. Well, there's different methods for it. Let's just look at the CP method. So we're going to estimate mean square error. Okay. The CP estimate of test MSE is computed by, well, not surprisingly, it has residual sums of squares in there. It has residual sums of squares. But let's just look at what it's doing, right? So imagine if this was nothing special. If this was nothing special, then we would have this. Right? What would this be doing? 1 over n, residual sums of squares over n. That's exactly what they said. Where is it? Right here. That's exactly what they said right here is MSE. Right? We would just be getting residual sums of squares over n. So this is like nothing's being corrected. Nothing's going on yet in the first square bracketed term. Now something's going to go on. Okay, now there's going to be some changes here. So when you're thinking about CP, you're thinking of what's it doing to that residual sums of squares estimate. Well, we have D predictors, so there's our D, and we have the variance here is an estimate of the variance of the errors associated with each response. So the variance here is estimated using the full model containing all predictors, okay? Containing all predictors. And what this CP is going to do is it's going to invoke a penalty. This is the bulk of what, the main point of what the CP statistic here is doing. It's taking your residual sums of squares, it's taking 2. Don't worry about 2. 2 is not important here. The formula is important, but 2 is not that important. What's important is the D and the estimate of the error. So try to think about how this formula is working. There's a lot of stuff going on just in this. Well, D is the number of predictors, right? D is the number of predictors. So let's say that I include a lot of predictors into this model. Like I include 100 predictors. Like I do like that researcher was doing, adding 15 predictors and then boasting about a 15% R squared. We weren't impressed by that, right? We looked at it as, yeah, on average, 1% per predictor, not very interesting. CP is trying to tell us that. It's trying to tell us that. It's trying to say, you know what, I'll do that job for you, and I will develop a measure that's going to include the number of predictors. So as D goes up, 2 times D is going to go up. As the number of predictors increases, you're adding a bigger and bigger penalty to this term right here. That's the idea of how CP is working. So what do you want for CP? For CP, lower values are good, right? You want lower values for CP. Higher values aren't good because higher values are just suggesting that you're adding a lot of predictors. Now, it may seem like it's bad to add predictors in, like CP saying, hey, don't add any predictors. No, no, no. Add predictors. But what does CP do? Hold you accountable. It says if you're going to add predictors, make sure they're worth something. Right? Make sure those predictors are worth something. Otherwise, you're going to get it. Right? You're going to get punished. And you think, punished? That actually sounds familiar. What other statistic punishes? Adjusted R squared. Same principle. So if you're going to add predictors, make sure they're worthwhile. That's what the idea of the CP is. The Akakis is a version of the CP. Okay, so it ends up being very similar, a little bit different. You can look at the changes, but 1 over n over here. The BIC is going to be a little bit different, and that's because it includes a log function here. Now, how that's going to work out is that they tell us right here that since log of n over 2 for any n greater than 7, the BIC statistic places a heavier penalty on models with many variables. So this is the active component here, where things start to, what they're saying here is for any n greater than 7. So at some point, this starts to invoke a heavier punishment for models with many variables. So it's a bigger penalty than the AIC. And the AIC is the one that we're often going to see in the literature and in regression reports. This is the one we're going to see. So BIC is like, don't add predictors. It's like an angry one, whereas AIC is not quite as bad. Now, AIC is kind of like this. It's like it's punishing your model, but this one is punishing it a little bit more severely, especially if you start adding in a lot of predictors. In both cases, AIC low is good. You want low AIC values. Okay, smaller is better. And same thing here. Smaller is better. But BIC will usually be smaller, will usually be larger rather than the AIC because it's punishing a little bit more. It's adding in this term. So usually the BIC is greater than the AIC because it's punishing a little bit more extensive. Both measures you want low though, but this is a little bit stricter, right? You can almost think of it like it's like the Chaffee test, you know. If you draw an analogy, Chaffee is going to be a little bit more, well, let's be a little bit, punish a little bit more than say like a Tukey, a little bit more stringent on that one over there. There's your adjusted R squared. And adjusted R squared may be familiar from previous courses on how that works. That's going to bring your R squared down a little bit. And again, the active component here is your D. There's different formulations for R squared. This one's a little bit different, but it emphasizes those D variables. And you can work through that. You can see what's going on in that function. That what's happening is that it's the same idea with the AIC and the BIC. As you add predictors, it's got to be worth something, right? It's got to have a reduction in the residual. Otherwise, it's not worth it. So This again guards against the researcher adding those 15 predictors or 20 predictors or 30 predictors and then boasting that they're explaining 30% of the variance or what have you. All of these are done on the training data, which serve as pretty good estimates of the test data. Okay. Which one's absolutely better? Well, they may behave differently in different cases, and they show a graph up here of what's going on with the different number of predictors and BIC and CP, et cetera. So even in this case, this is all for the credit data. And they're all kind of, they suggest a little bit different, right? So the CP is like 6 predictors, number of predictors gets the minimum over here. BIC gets the minimum at 4. Adjusted R squared over here. Now adjusted R squared, remember you want adjusted R squared to be big, right? That should be a big number. You want that to be big. These you want low. So that's why the graphs look like that. You say, how could the graphs look so different? Low, low, and you want this one to be big. But again, if you're going by adjusted R squared criteria, you're like 7 predictors. If you're going by this, you've got 4. If you're going by this, you got 6. That's why at the beginning I said, which is the best model determines on what criteria you're using to define the best. And sometimes you say, well, I just want to know what the best model is, and I just care about the data. Enough with the theory. Well, the theory is determining what the best model is, but they have different opinions. So if we don't unpack the formulas, right? If you don't know the formulas, and you don't know how it's being assessed exactly, then you don't know how best is being defined. And if all of these hinted at the best model, like the number of predictors was the same, like there was one universally best, and they all said 4 predictors, right? Imagine all these said 4 predictors. Well, then maybe we can say that's like the archaeological dig. We say there's a skeleton down there, period. But that's not how these things work. Best is defined by the criteria determined by how you're going to define best. And that's why knowing how that formula works is really, really important. Otherwise, you don't know when someone says best, you don't know by what criteria are they judging best by. What's the best of the best models? So it kind of gets a bit circular. Validation, cross-validation, we can do that as well. You can look at that. And we're now up to where I wanted to get up to, which is the shrinkage methods. And we will start here next week, and we will look at these things which take your residual sum squares, and what they do is they add a penalty term to your residual sums of squares, which is going to be this thing right here. And that is going to help us shrink some coefficients and help us choose the better model. Okay, so we're going to finish this up next time, chapter 6, and naturally we're going to get into principal components analysis, because the concluding parts of this chapter deals with principal components, but they don't really talk about principal components that much. So we're kind of going to be merging those 2 chapters as we go. So finish off chapter 6 and then into principal components, and we'll be off into factor analysis pretty soon, which will have to go outside of this book to treat factor analysis, which will be in the Mayer book. Okay, so that's it for this week. We'll see you next time.